We're going to work on using Gauss's law to find the electric field inside a uniformly charged sphere of radius little a. So we're going to say the whole sphere has a charge plus q and it's evenly distributed throughout the charge, throughout the sphere. Now outside the sphere, this looks just like a point charge, okay, because we can do it just like a point charge setup. So what I want to do is look at inside. So if I want to pick a spot, like X marks the spot of the electric field inside this, then again I have to do a Gaussian surface, like this, that mimics the shape, so it's a sphere, and I need it to be on the outside edge. So for Gauss's law, I need to draw my surface. So I've got my surface, and it has all the conditions. It's got the point of interest right there, that distance, that X marks the spot, so I want to find it at a distance r away. Okay, and so I've got my Gaussian surface. Now Gauss's law looks like integral E dot dA on the surface is equal to our Q inside enclosed over epsilon naught. So we're going to do first E dot dA, and then we're going to do the other parts. And on the outside part of the sphere, the electric field points radially out. It turns out that we can make the same sorts of arguments to say that our electric field is going to point like this, anywhere along in here. And the reason is that it doesn't matter what orientation you have in the sphere, everything looks the same. So if it oriented preferentially more in one dimension, it would mean there was a particular dimension that was the most, the charges were accumulated there or something like that. So the electric field points out like that. And similarly, we can say, of course, that the area at any point, so that's the area vector, this dA, is going to point in the same direction anywhere along this surface. Okay, remember it's a ball, a globe, a sphere. And so if you take that ball, then then A points radially out. So if we do that, we can say E dot dA along the whole surface is going to be E times dA. The angle between them will be 0 degrees. Cosine of 0 degrees is 1. We still have this integral. And then we would say, hey, anywhere along here, the same distance away from the center, again, because it's uniform and symmetric, the electric field had better be the same. So the electric field has the same value anywhere on the green surface. So we can pull that out. So we have E integral dA is still equal to this Q enclosed over epsilon naught. Okay, so integral of dA is just the area. So we want the area, but what area? It's not the area of the full sphere, it's the area of the green sphere. Area of green, not the black sphere. So that would be 4 pi, that's the surface area of a sphere, times r squared, because r is the radius of the green. So I have E 4 pi r squared equals Q enclosed over epsilon naught. Now, to find the Q enclosed, because we don't enclose all of the charge, because this plus Q is throughout the whole object, and we can't say it's just R over A or something like that. It is a fractional amount, but the way we do it is we use the idea of density. Right? The density is the same, whether we have the big sphere or the small sphere, the charge density. So on the big sphere, we would say that would be Q divided by the volume, 4/3 pi A cubed, because that's the big volume, must be equal to the Q enclosed over 4/3 pi r squared. That's the smaller volume. That's the green, right? So that's the volume of the green sphere. Because the charge is uniformly spread out in the volume, the density, the volume density, whether I have a big sphere or a small sphere, I should have the same charge per volume. So this is where our charge density, just like our mass density, comes into play. So if we look at that and we solve that for Q enclosed is equal to, well, the 4/3 go away, the pi's go away. It's equal to Q, I'm sorry, this isn't R cubed because it's a volume, R cubed over A cubed. So I need to stick that in this expression. So plugging that in, I have that E times 4 pi r squared is equal to Q r cubed over A cubed, and then there's a 1 over epsilon naught. Okay, so I've got an r squared and an r cubed, so those go away. That gives me just an r to the first power, and the electric field equals 1 over 4 pi epsilon naught Q r over A cubed. Now this we recognize as our usual K, so if you'd rather do it like that, it's K Q r over A cubed. Now, first thing is when r goes to 0, we're all the way at the center, there's no charge enclosed, then the electric field goes to 0, so that's nice. When r is equal to A, right, when we enclose the whole sphere, notice we get back to sort of what we expect. E equals K Q A over A squared, or E equals KQ over A squared, KQ over R squared. Once we're outside the sphere, none of this applies. Let me just quickly show you what happens when we get outside. So outside, because this is even easier, outside the sphere, because I made a claim about that, that's supposed to be a sphere. Here's my Gaussian surface. Woo, that's lovely, right? Okay, there's R. Then I do the same thing, integral E dot dA is equal to Q enclosed over epsilon naught. Here, this does the same thing it did before. It's exactly the same argument. So I get E times 4 pi R squared. E times 4 pi R squared is equal to, now the Q enclosed is just this plus Q. That's all the way through the sphere. It doesn't matter where it is. That's capital Q over epsilon naught. Our E is equal to 1 over 4 pi epsilon naught Q over R squared. So that's okay. E is equal to KQ over R squared. So it's just like a point charge, which I said at the beginning, but I didn't actually prove. So this is what happens. So if we look at the electric field, if we put all of this together and we plot the electric field as a function of R, here's where R is equal to A. Notice we start out with, at R equals 0, electric field equals 0. It increases linearly, right, because it's just a linear relationship. This is linear because it's KQ over A cubed. That's all a constant times R. And then this one drops off as 1 over R squared. But right at this point, they have, of course, the same value. So that would be my electric field of a sphere as a function of R. So it increases and then it drops off like that. Finally, we can say something about where charges are located in a conductor. Because if I have a conductor, so this I assumed was an insulator, and I want to talk about why I really wanted this to be inside an insulating sphere, an insulator, not a conductor. And this is the reason why. Because let's say I've got a chunk of conductor, right? And if we have an electric field inside the conductor, E is inside, so in the depths of a conductor, so like the conductor extends like this. So we've looked inside. So if there's an electric field inside the conductor, then that means that charges will move because they can. So if there's an electric charge that way, that's the direction plus charges would go. So minus charges would go the other way. So electrons would sort of head off in this direction. Well, when electrons head off in this direction, what it does is sets up an electric field in the opposite direction because there are positive charges sitting that are exposed, and we get to a zero electric field. So charges move until they don't feel any force, until they've rearranged, until we don't have reason to, I guess, or they hit the edge, so that the electric field equals zero inside a conductor. So the electric field inside a conductor is zero. And what that means is that if I have sort of a conductor shaped like that, if I draw a Gaussian surface, here's my green Gaussian surface, sort of right on the inside. Okay, I don't know, sort of a acorn shaped, I guess. I don't know, walnut shaped, but here's my Gaussian surface. Well, that's inside the conductor. And that means the electric field must be zero, because we said the electric field has to be zero inside a conductor. And so what that means is E dot dA, it doesn't matter what's going on with the dot product or anything like that, that's going to equal zero, which means that the Q enclosed is equal to zero. And so what that means is that any excess charges, if a conductor is charged, all of the charges sit on the outside of the surface. So when you have a charged conductor, so charged metal, all the charges sit on the outside. All the excess charges sit on the outside. And I think I made this argument before by saying, hey, these charges want to get away from each other. So they get as far away from each other as they can, which means they're really on the outside edges. But it's not like one is left on the inside like, hey, this seems okay to me. All of them go to the outside because we're going to have an electric field equaling zero. If there's one somewhere in the middle, then charges are going to move to try to get away from it, and that will then create an electric field or come to it. If there's a positive charge in the middle, then an electron's going to be like, hey, I'll hang out there, and it'll move and come to that spot. And so we have that for conductors. The electric field on the inside of conductors is zero, and that means that the charge enclosed inside a conductor is zero, or the charges all sit on the outside. And it doesn't matter the shape of the conductor. This is always going to be the case in an idealized conductor. Excess charges. I mean, there's still charges inside the conductor. Don't get me wrong. There's still positive charges because they're still material. They're just balanced by a negative charge. So there are no extra. Any extra charges sit on the outside surface.